We talked in our last class about partial derivatives, and we recognized that partial derivatives are slopes of tangent lines. The partial derivative with respect to x, which is, they give the definition here, f sub x, that's the slope of the tangent line at a point on the surface where the tangent line goes in the direction of the x-axis. The other partial derivative, f sub y, is the partial derivative of f with respect to y. Now that is the slope of the tangent line to a point on the surface going in the y direction. So these, so how do we find these partial derivatives? If we're going to take the partial derivative of a function with respect to x, we're going to hold the y values constant. If we're going to take the partial derivative of a function with respect to y, we're going to hold the x variable constant. Okay, so the notation for partial derivatives, there's a lot of different notations for these partial derivatives. And we talked in our last class, we did an example where we used the Newton notation and the Leibniz notation for a particular problem. And we actually finished that example. And I want to look a little bit, I want to look at one of the book examples. It was example 1 that we finished. So I'm going to go and look at example 2 here. Right. So in example 2, they give you a function, and actually that would be a paraboloid opening downwards, starting at its highest point would be z equals 4. They want you to compute partial derivatives, the two partial derivatives at the point 1, 1, and interpret the numbers as slopes. So the values of these, hold on here, the values of these partial derivatives are given here. So remember, the partial derivative of f with respect to x, that equals negative 2x. So if you look at the function above, if you treat the y variable as a constant and then differentiate, you're going to get that partial derivative. And when you evaluate that partial derivative with respect to x at 1, 1, you get a value of negative 2. Now, what does that mean geometrically? Let me show you. So in figure 2 here, they have, let me just move that up a little bit for you. In figure 2, they've drawn the surface, and the point when x is 1 and y is 1, then z equals 1. If you substitute in x equals 1, y equals 1 in that equation, in the surface, z would then have to equal 1. So the point on the surface is 1, 1, 1, and we draw a tangent line in the direction of the x-axis. And let me ask you, is the slope of that red tangent line there, is the slope of that red tangent line with respect to the x-axis, is it positive or negative? What would you say? Is the slope positive or negative? So hold that thought, Angela. So the slope, you have to look at the slope as, like, think of like you're skiing, okay? You're skiing on that tangent line, and you're skiing in the direction of the positive x-axis. So if you're skiing on that tangent line in the direction of the positive x-axis, I mean, remember when you learned about derivatives in Calculus 1, it was always with respect to the positive x-axis. So as x increases, okay, um, and we move along that tangent line, are we moving downward or upward? If we're skiing along the tangent line and letting x in the direction of when x gets larger, are we skiing downward or upward? We're going downward. That's right, IB. Angela, do you see that? Wonderful, wonderful. Okay. Well, so the slope's negative, and in fact, the slope equals -2 for that tangent line. That's the interpretation. Are there any questions on that? Okay. How did we get -2? The way we got that, IB, is right here. The partial derivative of f with respect to x equals -2. Okay. Wonderful, wonderful. Okay, well now let's look at the partial derivative of this function with respect to y. So you hold the x variable constant and differentiate with respect to y. So that function f of xy is 4 minus x squared minus 2y squared. If you differentiate that in example 2 with respect to y, you hold the x constant and you're going to get a -4y. So if you substitute in 1, 1 in there, of course, the x doesn't matter, but the y equals 1. So the partial derivative equals -4 at when x is 1 and y is 1. So how do we interpret that? Well, let's go down to figure 3. In figure 3, okay, they draw a tangent line to the point 1, 1, 1. Okay, and think of the slope of that tangent line as you move in the direction of the positive y-axis as y increases. Is the slope of that tangent line, does it appear to be positive or negative? So that red tangent line, I always think of like you're on a skis and you're skiing down this tangent line. It would be indeed, that's right, Yeva, that's right, Lexi, it would be negative. It would be negative. And because with respect to the positive y-axis, I want to say it the right way. With respect to, if you move in the positive direction on the y-axis, okay, you have to go downward on that tangent line. So the partial derivative is negative, and it seems steeper, right? It's that slope seems steeper than the slope, the other slope we looked at. And in fact, can you tell me what the value of that slope is for that tangent line in figure 3? That's right. Good, Norina, Lexi, and Matthew, -4. That's exactly right. So this is how we interpret these we call them first partial derivatives. This is how we interpret them. And, you're going to learn a little later on that we can actually find slopes of tangent lines in any direction. So we're finding with these first partial derivatives, we're finding slopes of tangent lines with respect to the positive x direction and positive y direction. But what if I wanted to go in the positive? What's the slope of the tangent line in, at the 45-degree angle between the x and y axis? There's a tangent line that goes that way in that direction. What's its slope? Okay, well, you're going to learn how to do that a little like next week. IB, you asked about -4. -4 comes from here. Partial derivative of f with respect to y equals -4. Okay. Okay, wonderful, wonderful. You're welcome. You're welcome. So let's go. Are there any other questions before I move forward? Okay. Well, let's look at an example here. Let's look at some more examples. Okay. So in this problem here, well, you have w is a function of how many variables? 3. Okay, that's right, Lexi. Well, you then would have 3 partial derivatives that you can find. 3 partial derivatives. Now, this is not a surface in 3-dimensional space. W is not a surface in 3-dimensional space because we would need a 4th dimension. Now, we could look at level surfaces by taking W and setting it equal to different values. But here we're just interested in computing these partial derivatives. Let me give you a moment to copy. Sorry, I think I was muted for a moment. Okay, so I don't know if you heard me on this. So what I have here is the Leibniz. I'm sorry. So remember the notation here. This notation is the Leibniz notation for partial derivatives. The Leibniz notation. And below it, I wrote the first partial derivatives using Newton's notation. Now we are interested, let's focus on this first partial derivative, the partial derivative of w with respect to x. That first partial derivative, what we're looking at how the function w changes with x. we're trying to understand how does that function change with respect to x? At what rate is the change? So in order to find that rate, what variables have to be held constant? What variables have to be held constant? That's right, Norina. You're going to hold the variable y constant. That's right, Matthew, and the variable z constant. Good, that's right, Abdullah. So let me show you how to compute that. So I like to use Leibniz notation. Now, again, you see how I'm doing this work. You see how I'm doing this work. Okay, so for your second exam, naturally, I want to see work like this. Okay, naturally, I want to see that. Okay, that's showing your work. Okay. All right, so I hold the z, the y, and the z constant. So this allows me to pull the z out of that partial derivative. And now I have to utilize the chain rule. The derivative of e to the x is e to the x. So e to the xyz power. And then I'm going to take the derivative of the inner function, which is x times y times z. But I'm differentiating that with respect to x. So I'm left with 1 times y times z. And so I end up with y times z squared times e to the xyz. Are there any questions on that? All right, well, let's go ahead and do the next one. So the next one we want to do, the next partial derivative is the partial derivative of w with respect to y. Partial derivative of w with respect to y, we're going to hold the variables x and z constant, right? X and z. So we're using the chain rule again, and we end up getting this answer. Please let me know if you have any questions. Okay, now now we're left with the last partial derivative, the partial derivative of w with respect to z. Now, if we're going to find the partial derivative of w with respect to z, what do you hold constant? What variables? We're studying how w changes as z changes, right? So we're isolating that effect. To isolate the effect, we have to hold the x and the y constant. Good. Good, Norina. Good, Matthew. So, okay. Well, here is the work for that one. So that's a little more complicated. Because the variable z is located in the first function z and in that exponential function. So we can't factor z out, because we're differentiating with respect to z. So we're going to have to use the product rule. And then, of course, the chain rule as well. Are there any questions on that? Okay. So when students get disconnected from the session, just come back in, and that happens from time to time. Okay. So now what we want to do, well, so we did an example now where we had a function of more than 3 variables. But we're not done yet. This is a large section. A lot of good stuff in here. Hold on. One moment, class. So in calculus 1, did you stop at just taking one derivative? So the first derivative gives you the slope of a tangent line. What's the second derivative give you? We needed to do second derivatives too in calculus, so we could talk about concavity. That's right, Lexi. And so if we go to the ebook here, well, we also have second partial derivatives in for functions of several variables, or more than 2 variables. And this is how the partial derivatives, well, I think I'll just make it a little bigger. So, well, it mentions above here, if f is a function of 2 variables, then its partial derivatives are also functions of 2 variables. And so we can consider their partial derivatives as well, which we call the second partial derivatives. And so you have all this notation here. For second partial derivatives. You have Newton's notation, and then you have the Leibniz notation. So they have these different kinds of notations because it's often convenient to, like in certain situations, one notation is more convenient than another. So let's take a look at an example. Okay, so example 6 says, okay, find the second partial derivatives of this function, f of xy equals x cubed plus x squared y cubed minus 2y squared. We want to find the second partial derivatives. Okay, well, the first partial derivatives are given here. That's the first step. You can't get to the second partial derivatives until you do the first partial derivatives. So there you have your first partial derivatives. Okay, so when they take the partial derivative of f with respect to x, they're holding the y constant. And when they take the partial derivative of f with respect to y, they're holding the x constant. And now, okay, let me just maybe highlight that. Okay, now we have these second partial derivatives. Take a look at it for a moment. Let's make sure you're comfortable. So you see how they use the Leibniz notation to help. It's certainly helpful, right? Do you notice that that there are four second partial derivatives because there's four orders in which you can differentiate. The f sub xx and the f sub yy, those are second partial derivatives with respect to one variable, and those would correspond to concavities. So you can have concavity at a point on a surface with respect to the x direction, and concavity at a point on a surface with respect to the positive y direction. So think of a point on a surface. Think of there's concavity in the x direction and concavity in the y direction at that point on the surface. But the mixed partials, the f sub xy and f sub yx, those are equal to each other in this example, and it's no accident that that's the case. The second mixed partial derivatives are always going to be equal, and that's by a theorem called Clairaut's theorem. Okay, we call that Clairaut's theorem, and I'll just show it to you real quick. This is that result. So we won't worry about it. It's not hard to prove. But they talk about, well, okay, we can find, can we find higher partial derivatives? And the answer is yes, we can. Look at this. If you wanted to find f sub x, y, y, okay, that the order in which you would differentiate would be, you would do the, I want to say it the right way. Let me show you this, how I do this. Hold on. This is fine, but let me bring up the whiteboard here. Okay, so one moment. So this third partial derivative, okay, this is a third partial derivative. Okay, So I like to think in terms of like trying to think of it like the way like if you had, for instance, just as an example, 2 to the 8th power raised to the bth power, that would be 2 to the a bth power, right? So I like to think of like multiplying exponents, even though I don't have exponents here. This is this second partial derivative, sorry, okay, then like that. And then this, the inner part here, you can think of it as like, hold on, I want to make sure I'm doing something wrong here. Wait, hold on. Yeah, yeah, okay. And then, yes, Lexi, I was going to get to that. One moment. Okay. So when you do, I always think of like math operations. When you have parentheses, okay, which parentheses do you do first? Which ones? So what I want to do is this here, this is Newton notation. That's right, Ivy. This here is Newton's notation. And I want to get to Leibniz notation like they show in the book. But I don't want to get confused, right? So what helps me a lot, okay, is, okay, I mean, based on like how I treat exponents and with parentheses, are we good with this part? Are we good with this part? Give me a thumbs up if you're okay with that. All right, good, good. All right, well let's get to Leibniz notation. So I have these parentheses here, and as IB says, normally you do inner parentheses first. So this is a third partial derivative of this function. But what order am I taking the partial derivatives? Well, I'm going to do the partial derivative with respect to x first because it's it's the center. It's like the inner parentheses. And then I follow that up with a partial derivative with respect to y and another partial derivative with respect to y. This could be denoted also this way in terms of notation. You could denote that way. Okay. And you could even denote that, this way. You could write this like this. See? One moment. function. Yeah. See how that works? Leibniz notation really, I mean, how many like Leibniz notation? Perhaps. For this kind of situation. How many like Newton's notation? Okay, Matthew likes Newton's notation. All right, well, Lexi likes Newton. Let me just see if there's, okay. And incidentally, you could also write this like this in Leibniz notation. Okay, they all mean the same thing. And the reason we need these higher derivatives, well, remember when you learned about Maclaurin polynomials and Taylor polynomials back in calculus 2? So if you want to approximate a function at a point using a polynomial, you could do a first degree polynomial, second degree polynomial, third degree polynomial, and so forth. That should hopefully ring a bell. Yeah, that's right, Norina. And you needed those higher derivatives in order, if you're doing like a second degree Taylor polynomial, you need to go out to the second derivative. Third degree Taylor polynomial, third derivative. So you take functions of one variable and approximate them with polynomials. Well, here in multivariable calculus, we can actually take surfaces and approximate those surfaces by other surfaces that are like polynomial surfaces, so to speak, like a paraboloid, for instance. And that's why you need these higher derivatives. Okay, now we're gonna basically in section 11.4, we're gonna look at surfaces and approximate the surfaces at a point with tangent planes. But for sure, you can go further than that, and that's one reason you need these higher partial derivatives. Lexi, you asked, that was a good question you asked. Okay, comfortable? All right, wonderful, wonderful. All right, let me do one more. I want to do one more example with you here. One moment. Just got to find it. One moment. Hold on. Just got to find it. Okay. Implicit differentiation. How many recall doing that in calculus 1? Implicit differentiation. Yeah, Yaver remembers it. Alberto remembers it. Okay. Well, so, you know, here we're given a equation that relates the variables x, y, and z. It relates them. Okay, and we understand that z is implicitly a function of x and y. Z is implicitly a function of x and y. But we can't isolate z and write it as a function of x and y. But we know as x and y change that this variable z changes, and so we ought to be able to find these first partial derivatives. What we ought to be able to find the rates of those change, the rates of change. If we regard z as a function of x and y, we can do that again, because this equation, if you give me if you change x and y and then solve for z, well, if you give me an x value and a y value, you can solve for the z value. And if you change the x value and the y value, the z value will likely change. So z is implicitly a function of x and y, and therefore, as z changes, as x changes, z changes at some rate, and as y changes, z changes as well at some rate. So we have to use implicit differentiation. But of course, it's a little more. I mean, the concept that you learned in Calculus 1 works here. We just have to be a little. We have to be a little bit careful. So let's do the implicit differentiation. Okay. So first, we want to find the partial derivative. We're gonna try to find the partial derivative of. Hold on here. We want to find the partial derivative of z with respect to x. So I'm going to take this equation and differentiate both sides with respect to x, but it's partial differentiation. Okay, so that's what happens in the second step. Okay, so now we go ahead and we differentiate both sides. Well, the partial derivative of x with respect to x, I mean, what do we, this here on the left, this here on the left is just the partial derivative of x with respect to x minus the partial derivative of z with respect to x. Well, the partial derivative of x with respect to x is 1. And so I get 1 minus the partial derivative of z with respect to x here on the left side. Now on the right side, I'm taking the partial derivative of this arctan function with respect to x. So on the right-hand side, what rule are we utilizing here? I mean, if we just think about the derivative of the arctangent, that's right, Alberto, very good. Derivative of the arctangent is 1 over 1 plus x squared. So we're using the chain rule here. The outer function is the arctangent, and then the inner function is y times z. But I don't do that all at once. I get here, and then I do the partial derivative of y times z with respect to x here. And for there, I'm gonna use the product rule. So of course, in the product rule, we're treating y as a constant. Okay, we're treating y as a constant. Z, we implicitly understand as a function of x and y, right? So z is a function of x and y, and so z is not, we can't treat z as a constant, And we can't treat x as a constant when we're differentiating with respect to x. But we can treat y as a constant, right? So we get here. Right, because z is a function of x and y. We're differentiating with respect to x. So z can't be treated as a constant at all. But we treat y as a constant. So, okay, we get down to here. And now we are going to isolate the partial derivative of z with respect to x. And this is you learn this in implicit differentiation to, now that we have, we're looking for the partial derivative of z with respect to x. So I have to get that on one side of the equation, which I do. I add this term here, this partial derivative, to the right side of the equation. And then we factor out the partial derivative of z with respect to x. And now all that's needed is dividing through by the both sides of the equation by y over 1 plus y squared z squared plus 1. So that we can, get the partial derivative of z with respect to x. Of course, if we want to simplify this expression, okay, I can multiply the top and the bottom. Let me just remove this here. So this here, if I multiply the top and the bottom by 1 plus y squared z squared, we will get this answer here. That's your partial derivative of z with respect to x. Now, naturally, on this next exam, I'm going to want to see these steps. Okay, I'm going to want to see these steps. That's justifying your answer. So if you get the right answer, but the work's not there, you're not going to get credit for that work. All right. Now the next one, are there any questions before we move forward here to get we still have to get the partial derivative of z with respect to y. What are you going to hold constant, by the way, for the partial derivative of z with respect to y? What do you hold constant? What variable? Right, you hold the x constant. That's right. So let's go to the next page. Same approach, only now we're differentiating both sides with respect to y. I'll mention too, class, I'll just mention this in passing. So I know that, well, no, let me let you. So I didn't show all the steps here, but you can show that the partial derivative of z with respect to y equals negative z divided by denominator y plus 1 plus y squared z squared. So I'll just mention this in passing. You know, I know that, of course, well, I'll mention it. I'll mention it after I'm done here. I'll mention it after, because we're going to take a break in just a moment here. Who's feeling good so far with this section 11.3, partial derivatives? Who's feeling reasonably good? Okay, or is. Of course, you have to do some practice, right? But let me see here. Hold on. Somebody said something here. Yeah, well, this partial derivatives are utilized a little bit in differential equations for to prove some of the theorems, at least at Montgomery College. By the way, I'm teaching differential equations in the fall. In the fall, I'm teaching linear algebra, that's Math 284. I'm teaching differential equations, that's Math 282. Okay, so you'd certainly be welcome to join the class. All right, any questions before we stop the recording? Okay, Alex is good. Noreen is good, wonderful. Okay, excellent. I'll stop the recording.